Hello. So this is a makeup lecture for the lectures I missed the week before the last one. The first one, so this lecture will be a continuation of the topic that we discussed on Thursday, which was the ideal class group. And to remind you, the ideal class group can be defined in two equivalent ways. One is you define an equivalence condition on ideals in R. So the R is numbering. R numbering. Then I don't know why I use capital letter ring. So the equivalent if AI is equal to Bj for some AB in R. Okay, so then you can multiply ideals in the usual way and the equivalence condition continues to hold. Then you get a group, and that's the class group. Equivalently, you can define fractional ideals, in K. So these are ideals of the form 1 over d I, where I is an honest ideal in R. So then you can multiply fractional ideals and you still get a fractional ideal. You can also you can show that every fractional ideal has an inverse in the sense that there will be some other ideal such that you multiply these two and you get the whole R. And then you take the principal ideals inside of the fractional ideals and you form a quotient of all fractional ideals of R modulo the principal ideals, and that gives you again the class group. So this I defined in all details during the last lecture, and we also proved that the class group is finite. So the main theorem was that class group of R, sometimes this is also denoted the class group of K, just is the same group, is finite. So it's a finite abelian group. Alright, so and the proof is kind of gives you a method for finding what this group is. Just abstractly, if I tell you that this group is finite, it's not clear at all how you would go about computing it. But the proof has two steps. So proof, first you show that any non-zero ideal in R contains an element alpha such that the norm of alpha is less or equal lambda n I for some universal lambda that depends only on R. So some lambda depending only on R. Okay, and then once you have this result, which is the key result, it's not hard to show that every ideal class so this was the first step, and then the second step, every ideal class contains an an ideal inside of R such that the norm of I is less or equal lambda. Okay, and from this you immediately conclude that the group is finite because, well, the number of ideals of given norm is finite. That's easy to show. Okay, so now if you look at this kind of gives you already an approach to computing the class group. Well, what's the approach? Suppose it's reasonable to believe that you can compute all the ideals given enough time and computational power. You can compute all the ideals satisfying this property if I give you a specific lambda. Okay, then this fact tells you that, well, then you get a set of generators for the ideal class group. This is not enough to conclude what the class group is because you have to also determine the relationships between the generators. But what will be happening, essentially, you can try to factor or find elements of small norm in R, and then you can factor them into primes, and that will give you certain relations. Okay, so we will now do what we will do. I will describe this process in more detail, and then give several examples that show how this works. Right, so what's the method? How to compute class group of R. So suppose we are given an explicit lambda. Okay? Alright, so the first step would be find all prime ideals of R whose norm is less than lambda. Find all prime ideals in R of norm less or equal lambda. Okay, then the second step would be find elements in R of small norm, whatever this means. We will see on examples what exactly we're trying to do, of small norm, and factor them, and factor alpha into primes. Alright, so this alpha should have a norm such that the norm is smaller than lambda. Okay, so suppose you can find such alphas, then if you factor them, the primes that appear in the prime factorization will be exactly the primes in the first part, because the norm of alpha will be the product of the norms of the primes that appear in its factorization. Right, so then suppose I have produced, so here's an example, or the idea of how this works. Suppose I produced maybe P1 and P2 and P3, okay, which are in the first step. So these are among the generators of the class group. And suppose I find some alpha, and this alpha is equal to P1 squared P2. Right, so what does this mean? Well, this means that the class of P1 squared times the class of P2 is the identity in the class group, because I got the principal ideal. Okay, so then this means that P2 is the inverse of P1 squared. Okay, so there is a relationship, which means that this P1 can be used to produce P2. Yeah, because right, because well, maybe not exactly. You can produce P2, but this does give you a relationship. So if you produce enough such relationships, then having a finite number of generators and enough relations, you will be able to conclude what the group is. Of course, this becomes harder and harder more ideals you have from the first step. So that means that it's very important to have a good lambda. Good lambda that kind of optimal for most number rings, meaning that if you compute the prime ideals of norms more than lambda, then you essentially obtain the minimal set of generators. Now, do we have such a lambda? Well, we have some lambda that dropped out from our proof of the finiteness, and that lambda was the following. So you choose a basis. We have an explicit lambda from the proof of finiteness of class group R. And what was it? Well, we choose a basis of R. And then this lambda can be taken, let's see, what was it? Right, so you have these embeddings of K into C, and then lambda can be taken to be the product of I from 1 to n, and then the sum of absolute values of I of j. So you take the absolute values and here j runs from 1 to n. So here's an explicit number. We definitely can find the basis of R. There are algorithms for doing this. So, alright, so this is an approach for computing the class number. Now, the bound that you get out of this is not optimal by any means, and even for small fields, it's rather large, as we will see. So, an important result is that this lambda can be substantially improved, and this is due to Minkowski. So what is Minkowski's lambda? Minkowski's bound. Before I give the bound, I need to give you one extra definition. So an embedding K into C is real if the image of K lies inside of the reals. Well, sort of reals being the real line inside of the complex plane. Okay, and is complex if this does not lie in R. Okay, so now if you have a complex embedding, then the complex embedding comes with a conjugate pair. Every complex embedding has a conjugate pair, sigma bar K, which is also an embedding. Okay, so what's happening? So you embed this field into C, and then you apply the complex conjugation, which is an automorphism of C. Okay, so that gives you another embedding of K. And because K does not lie inside of R, the complex conjugate embedding will be genuinely a different embedding. Alright, so then you can sort of group all embeddings into two parts. So let lambda 1, lambda r be real embeddings of K, and then tau 1 bar, tau s bar be complex embeddings. Where I also group each complex embedding into pairs. Okay, so then what's the relationship between R and S and the degree of K? Well, we know that the number of embeddings is exactly the degree of K over Q. So that means that N is equal to R plus 2S. Okay, so this is the relationship between these numbers. So these R and S appear in Minkowski's bound. And now let me state what is Minkowski's lambda. So let's call M. This will be Minkowski's bound. It's the following number. It's 4 divided by pi raised to power s, and then n factorial n divided by n's power, and then the absolute value of the discriminant of r, and you take a square root. Right, so then this is a possible lambda. The same theorem, meaning that every ideal class an ideal I such that norm of I is less or equal than m. And we will see that this m is substantially better than the previous naive bound. That you can actually take this m as a bound will be a different issue that we will prove next week. We will probably start, maybe I will have time today to discuss how the proof goes, but now I just want to give you some examples how you compute the class group. So let's start with the simplest case. The simplest case would be the integers, but let's not do that. Let's take example. Let's take R to be Gaussian integers. This is one of the simplest number rings. We know that this ring is a PID. It's even a Euclidean domain. So the class group, of course, is trivial. But what is Minkowski's bound? Well, Minkowski's bound, and I will, maybe I want to, let me write this here so that it's always on the board. And I'll use a red pen since I have it. 4 pi s, and then n factorial, n to power n, and then square root of discriminant of r, and the absolute value. Alright, so let's keep it here. What is that? Well, obviously, there are two embeddings of R, and they are both complex. So this does not embed into the reals. I should have said when I was defining the number of real embeddings and complex embeddings, well, how can you define these numbers without ever mentioning embeddings in more elementary terms? The definition could be the following. If so, K can be defined in terms of some element, some algebraic element, and f x minimal polynomial of alpha. Okay, so then the degree of f is n, and it is irreducible. This is degree of f is n, and f irreducible. So then you can look at the roots of f, right? What is an embedding? An embedding is basically a choice of a root of f. So R is the number of real roots, and then 2s is the number of complex roots. And of course, if some complex number is a root of f, then its complex conjugate is also a root, because f has coefficients in Q. So this belongs to Qx, right? So the complex roots come in pairs, in conjugate pairs. So that's kind of the more elementary definition of R and S. And here the roots are, of course, my polynomial is this one, and the roots are plus or minus I, and they're both complex. So there are two complex roots. So R is 0 and S is 1. Okay, so then what is M? M is 4 divided by pi 1, and then I have 2 factorial divided by 4, and what's the discriminant? Well, discriminant is 4. the square root of 4. So this part disappears, and 4 divided by pi, this is less than 2. So this is less than 2. Alright, so then we have to look at primes whose norm is less than 2, which means we are looking at primes whose norm is 1, and there are no such primes, which immediately implies that the class group is trivial. So just from the bound, the class group of R is 0. So this is a different proof of this ring being PID, but the bound is of course much deeper than the fact that this is a PID. So this was a silly example, but now here's a more interesting example. Let me erase this. Next example is, let's take K to be Q adjoining square root of 23. Alright, now first we have to compute this number. Now this is a real quadratic extension, which means that S is 0 and R is 2. Okay, but R does not appear in this formula. So then this will be 1. This is obvious what it is. What's the discriminant? Well, the discriminant of a quadratic extension of this form, it's either this number or 4 times whatever is under the square root. And whether 4 is there or not depends on the residue of 23 mod 4. Well, 23 is congruent to 3 mod 4, which means that the discriminant of R is really 4 times 23. Alright, so then plugging everything into this formula, we get that this is equal to square root of 23, which is approximately, well, this is less than 5. So it is approximately 4 times 8. So we have to look at primes whose norm is less than 5, strictly less than 5. Now, if I didn't have Minkowski's bound, let's see what I get by that more elementary bound, which for which I need a basis. So an obvious basis of R is 1 and square root of 23, which means that this lambda that I get by my formula at the beginning of the lecture would be 1 plus 23 squared, and this is approximately 33.6. So now imagine, instead of 1, 2, 3, 4, here you have to figure out all the primes of norm up to and including 33. This is really heavy work. This is much easier. So you can see that the substantial improvement, and also since you are getting a substantial improvement, it indicates that this bound is much deeper than obtaining this bound. And in fact, we will have to work quite hard and introduce a new technique to prove this. But coming back to the same examples, so what do we need to do? Well, explicitly, how do I find the primes whose norm is less than 5? Well, let's just take the numbers 2 and 3 and factor them in R. The primes that have norm less than 5 definitely appear in that prime factorization. So that will include the primes that I need to generate my class group. Alright, erasing this part. So 2, how does this factor? Well, we know that 2 ramifies because the discriminant of R was 4 times 23. It is divisible by 2. So 2 ramifies. It's some p squared. And the norm of p will be 2 because the norm of 2 is 4. But what is p? Sorry.